All right, folks, how we doing? How's it going? Good. Ready for that CTF? I'm going to help you with that CTF today. We're going to be talking about memory safety, and it's going to help you in that CTF. All right, it's taking a really long time to change slides, bro. Why is it doing that? All right, have you ever seen one of these? You ever seen one of these guys? A little crash dummy action. So this is a fun fact about crash dummies. They're actually really expensive. So when they do these tests with these cars, they retrofit these little guys with all these doodads that track like their stats or whatever, you know? And so when they go crashing into a wall or something, they'll have like a sensor on their hand and on like their neck or something so that when these things happen, you know, kind of how bad it is. Safety is a really big problem, you know, in the industry, right? There are consumer expectations about it. There's regulatory expectations. People, when they use things, they kind of expect them to work and work well. And a lot of these expectations are not well defined. The other thing that's true about safety is that technology helps, right? Like the more you spend on technology, sometimes it helps you make better decisions about where you need to spend time developing. And the most important thing about safety crash dummies is that they actually do keep people safe, right? Like driving is so much safer now than it was in like the 1990s, and it's much safer then than it was in the 80s and 70s. I mean, like the Ford Pinto was like a death trap. Now we have like a lot of crash space and things are pretty good. But of course, like safety is very expensive and it's very sometimes difficult, and you can't let the solution be worse than the problem, right? You can do all these nice measures, but sometimes it's just a pain. You don't want to go on the school bus and wear a helmet to school because that sucks. So there's like reasonable limits to safety, right? And I promise when you reach the end of this presentation with me, you'll understand what that means in the context of security, because when we talk about security and the various systems that we trust every day, there's a lot of money being spent and there's a lot of work being done, but in the end, it doesn't matter if it makes things worse to use. So let's talk about memory safety. Memory safety is this big topic in the industry. We've had this problem for a very long time. It's one of the oldest issues in computer science, right? On its own, this whole topic is basically responsible for like the birth of the computer security field, because these memory safety issues were really big, and they still are really big, and they cause tons of damage every year on their own. And really, it's also one of these problems that, you know, despite like half a century of work, the better part of a century, we still have problems of memory safety in tons of applications around the world. Every day, new, you know, vulnerabilities are scanned for and found, and these vulnerabilities are often like really high severity. So let's actually talk about what memory safety is. So memory safety is the state of being protected, as in you don't have this problem, from various software bugs and security vulnerabilities with memory access. So we're talking about buffer overflows, dangling pointers, heap exploits, all that stuff that you hear about. And so, for example, you have this concept of memory safety in certain languages like Java. Java is memory safe because it does a whole lot of error checking to make sure that you don't have these problems. But by comparison, other lower level languages like C and C++ are not considered memory safe because they don't have these protections. Now, there's a lot of C++ fans that would be very quick to tell you that they have a lot more protections than C, but in the end, like you can still write memory on safe code in C++, and for the most part, you can't in Java. Basically, if you're doing like direct memory accesses, like with no bounds checking and all that fun stuff, you're going to have like memory unsafety. And so in a couple of rules, it means that you allocate your memory when you need it, you free it when it's not, and then you don't use any invalid stuff. That's pretty much the whole thing. And so, for example, some unsafe languages would be like C++, C. There's other languages that are new, like Zig. That's all I'm going to talk about, Zig, in this talk, so save it if you're into that. But there are a lot of languages out there that don't have any of these checks. And there are some other ones, but they're, these are the bigger and newer ones. Here's a stat for you. About 70% of vulnerabilities are due to memory corruption. It's actually really interesting how I think sort of true this generic statistic is. Like for Chrome, it's about 65 to 70% of vulnerabilities, I think, in 2021 were from memory corruption. Android, it's about like 60 to 70. On some devices, it's like 90%. of these vulnerabilities are from memory corruption. And iOS, it's pretty much the same story. Around 70% of these are, all coming from memory corruption issues, C and C++ code for the most part. And these are vulnerabilities too. So we're not talking about like data breaches. For the most part, when we talk about big data breaches like Equifax, Uber, there's tons of them out there. A lot of them have nothing to do with memory safety issues. They're like social engineering exploits and stuff. But a lot of these vulnerabilities are still really relevant because they'll be used on like individual people, so human rights activists, journalists, that kind of thing. And so, for example, there are a lot of memory safety exploits out there. Pegasus is a really big one. So for the longest time, and I think maybe even still now, a certain group worked on this tool that is basically a zero-click exploit. You send a text to an iPhone, and you own that iPhone. They don't have to open up the text. They don't have to do anything. They don't have to call you or whatever, pick up the phone. Doesn't matter. As long as their phone's on and they receive that text message, they just get popped. So it's a pretty bad bug. Several bugs, actually, that were present in like iOS and iMessage. Apple's known about these problems for a while, so they implement sandboxing. And these groups still try and escape those sandboxes. They do low-level kernel exploits and just own your phone. Anybody here heard of like Heartbleed? Raise your hand if you've heard of Heartbleed. Heartbleed is another memory safety issue. Lets you read more memory than you actually got. So it just lets you basically leak memory from OpenSSL. OpenSSL does a lot of sensitive things on the internet, like TLS. So you could theoretically and actually in practice leak keys through Heartbleed. And then WannaCry, like one of the biggest, probably the biggest still, I think, ransomware event, was spread with Eternal Blue, which is an SMB exploit based on a buffer overflow vulnerability in SMB in Windows. So these vulnerabilities are like massive. They have extremely high severity. These are like the really spooky stuff, like zero click, just send a packet or something to a device, and it's owned. So even though you might not hear about these a lot in like the news, a lot of people have to deal with these vulnerabilities, and they present real significant safety challenges, especially when it comes to like embedded devices and a lot of other specific applications. So you might be wondering, like, why is this still a problem? I took this class in Python, I took this class in Java, nobody told me about memory safety, I never had to worry about it, like, is this a real thing? It is a real thing, and the truth is some languages solve it and other languages don't. And so we're going to talk about how they solve it and what they do to kind of mitigate these issues. In terms of Python and Java and other like scripting languages, they, for the most part, most languages actually, including Go, which is not really a scripting language, use what's called garbage collection. So we're going to talk about what that is. So with the idea with garbage collection, at a high level, when you want to allocate your objects, you just allocate them directly from the memory thing. You say malloc or whatever, and gives you a certain amount of memory back, and you just go from there. The next thing you have to do is drop the pointer after the object is like done. So once you're done with the object, you drop it, you free it. Basically, the freeing part is implicit in this case. All you're doing is when your function ends, if you have a pointer, you just get rid of it. And so it does this thing called reference counting, where basically it sweeps the whole memory every couple minutes, maybe every couple seconds, sweep everything. And if there are any objects out there that have no pointers, in other words, nothing's pointing to them, no one's using it, you just deallocate those. And also, to keep memory safe, you want to do bounds checking whenever you access those things. Okay. It would be possible to implement your own garbage collector in C. Yeah, so garbage collection, there's a lot of algorithms out there. There's like whole textbooks or whatever, or like half of textbooks or whatever about this topic. Tons of different algorithms for like speed, efficiency, depending on what you're doing. But for the most part, the idea with garbage collection is that it's out of the programmer's hands. The language handles it, the runtime. You don't have to worry about doing all this memory management in like Python or Java. Additionally, there are some runtime protections in a lot of these languages. So once you're done with a pointer to an object, you just zero out the data. You null out the pointer so that it doesn't point to anything anymore. Nulling out a pointer is very important when you free it, because if someone uses that pointer, it'll be null and then it'll crash, which is a lot better than having it potentially be exploited. Additionally, you're doing this bounds checking, like don't store more stuff than a buffer can hold. And generally speaking, you don't want to do pointer arithmetic if you're trying to stay memory safe, like you try and abstract that away so that the programmer is not like adding 1 to pointers or whatever. So let's talk a little bit about the problem space. Memory safety is a really big area. There's a lot of different topics about it, a lot of different solutions to the whole idea, but you have to kind of know what you're getting into. And so basically there's two kinds of memory safety issues. There's spatial and temporal. So spatial memory issues are when you access memory in the wrong place. So if you do a buffer overflow, maybe you overflow that buffer, you write too much data, maybe you read data that's outside of that buffer by accident. That can be like information leakage. So all that falls under spatial memory safety issues. So like buffer overruns, like null pointer dereferences. If you use Java, maybe you've also gotten a null pointer dereference. That's not because Java is not memory safe, that's just because Java kind of sucks. Temporal memory issues are another type. This is when you access memory with the wrong type. So every single time you allocate an object in Java, for instance, that object has a type. It's a different type of object. One's a cat, the other one's a dog, or whatever they're doing in class these days. There's some kind of type associated with that. And that type tells you really important stuff. It tells you how much space you have. It tells you what methods you can call, all that kind of stuff. And so temporal memory safety issues are like type confusion. Raise your hand if you've heard of like use after free. Tenchi did a presentation on use after free. We'll explain that. Double free is another variant of that. It's pretty much the same thing. And there's other issues with that. The main thing you want to take away is that spatial memory safety is relatively easy. It's just bounds checking for the most part. So it's, for the most part, a solved problem. These are not the vulnerabilities that are affecting the iPhone or like Google Chrome and stuff like that for the most part. You'll still have issues with spatial memory safety, especially on like embedded devices that don't have these kinds of protections. But for the most part, those protections are relatively easy to implement. Temporal memory safety is where it gets difficult because all of a sudden you need to keep track of every single pointer in the program and make sure that it's pointing to a valid piece of data at any time, which is actually a little bit more difficult than it sounds. So let's talk a little bit about use after free vulnerabilities. So just for a little bit of review, when we're talking about memory safety in the context of C, you can do two kinds of things. You can allocate data with malloc, usually, and that returns a pointer to allocated memory. So if that works, it's going to give you a pointer, and it says, if you malloced like 10 bytes, it's going to give you a pointer back, and you can safely assume that that pointer has 10 bytes of space. That actually is, for the most part, fine. And then free is another function. When you're done with that space, you're supposed to free it. And what freeing does, and this is all it does, is it tells the allocator what gave you your memory in the first place, that that allocation is no longer in use. In other words, you can use it for something else. It does not zero out the memory at any point. That data is still in RAM. It doesn't actually change it. It just tells the allocator you can write something else there on top of it. And it doesn't set the pointer to null. So if you pass a pointer into free and then you use it later, it's still going to be pointing to a valid memory address, which might be a problem for you if you don't check it. So it can still access the data. I mean, if you free something and then you run another line of code to like access that pointer, for the most part, as long as you're not doing multi-threading, that data is still going to be there. And so that kind of leads us into this problem of use after free. Technically speaking, use after free is not necessarily insecure on its own, maybe. Because you could access that memory and it's just data, right? You're accessing it after you freed it, but it never got overwritten, it never got set to anything. That pointer never got set to null. It's not necessarily insecure on its own. You could be reading garbage. You could also technically be reading sensitive data if that's used somewhere else. And so we're going to talk about that with an example. But it becomes a vulnerability when that memory is then reallocated somewhere else. Because that means you have two pointers that both think they're pointing to two different things that are actually pointing to the same thing. So let's picture a login system for an example. I'm not going to do a lot of code in this presentation. This is all we'll see for the most part. If you've never done C, all this means is we're allocating an object, like in Java or Python. And that object is 15 bytes long. That's very important. It has 14 bytes for a username. And then it has a 1 byte Boolean to tell you if that user is authenticated to the system or not. But this could be any kind of thing. It could be a function pointer. It could be an integer, really any kind of data type. The really important thing that I want you guys to keep track of is that this is exactly 15 bytes. I mean, in reality, it might not be in our runtime, but for this example, we can safely assume it's 15 bytes. And so far, so good. We can allocate a structure for that. We get a pointer back to it. And then you can free that pointer. So basically, in the middle there, you're doing a bunch of stuff. Maybe you log in a user, do all that stuff, and then at the end, you free it. And as long as this is the end of that pointer's life, you're good. Just don't reuse it unless you malloc it somewhere else, but that pointer should be, after you free it, like unused. The problem, of course, use after free, is when you use it. So let's say we freed this variable and then we try and access it. Maybe it's like a while loop or something else, another function. But for now, this is still actually not a huge problem because even though we freed that vulnerability, this is the whole program, it's not a huge issue because technically speaking, we never set auth pointer to null. It still points to the same memory, just that the allocator thinks that memory is free. So the big question is, what happens if we allocate something that's something completely different that's of the same size? So this is the largest example we'll go through. Let's consider someone tries to allocate a string. Maybe you're running a web browser and you want to take some input from the user. You allocate a string that's 15 bytes. That's all you need. What happens is the allocator, when you freed that pointer on the second part, it said, yep, this space is free, and it has 15 bytes. So if you have any data type that uses it or less, you have one right in the hopper. Your allocator does this for performance reasons. When you free something, it assumes that you're not using it anymore. And so it hands it back to you because it wants to be fast. If you have another bucket that's free space, it's willing to give it back to you for another data type. And so let's say that we copy a string into this string buffer that's actually technically 1 byte over, but we'll ignore that for now, 2 bytes really. And this is just going to set it on to some name or something like that. This could be anything, by the way. It doesn't have to be a string. It could be an integer pointer. It could be a pointer to another struct or anything like that. And so this auth pointer thing now points to a string. In other words, if you were to go to a debugger and be like, print out what's at that address, it's going to print out AAA, BBB, all that stuff. And what happens here is string and auth pointer both think that they're pointing to unique memory, but they're actually pointing to the same place. One part of the program thinks it's a sensitive authentication structure. The other part thinks it's a regular string. And so by setting the last character to D, in this case, because remember that struct is like the username and then a single Boolean at the end, true or false, it sets that last Boolean at the end of that struct to D. And if you look at an if statement right there, D evaluates to true because it's non-zero. And so in this case, we end up going into our function here that we didn't want to access at the end. And so the problem is we have 2 pointers pointing to the same location in memory. The actual vulnerability is that one part thinks it's very sensitive and it's not going to be edited by someone else, and the other part thinks it's a string. So yeah, long story short, we have global thermonuclear war. I want to take a second real quick, and I'm going to enable something that I forgot to enable. I don't know if they see that. You can now ask questions. So if you want, you can go to that URL and you can ask any questions. I meant to enable that at the beginning. But so yeah, that's what use after free is. It's a basically type confusion, 2 places pointing to the same location in memory, and one has different permissions than the other. So yeah, long story short, we have global thermonuclear war because we didn't check our pointers, which is kind of an L. So yeah, this is not a huge hyperbole. There's a lot of embedded devices that run C code, a lot of programmers that don't catch this stuff. A lot of this code is like 50 years old. So yeah, have fun. Now we're going to talk about solutions because in reality, all we did was call a function in this example. But in practice, we overflowed into a Boolean, not a huge deal. But you could overflow into a function pointer, and maybe that function pointer then gets called. Now you have an attacker controlling the execution of the program and saying, hey, I want you to call this function, which is obviously a really big problem. And that's where a lot of these vulnerabilities come from. That's why someone can send a malformed PDF with a .gif extension to your iPhone and then own your iPhone because they're overwriting some function pointer, they're changing the execution of the program and running their exploit code. So there's basically 2 kinds of solutions to memory safety. You can apply it at the software level or at the hardware level. Software security, for the most part, is a lot bigger space, but there's a lot of really awesome hardware research going on too. And if we were to break down software solutions, they basically come into 2 camps. They either run at compile time. When you're writing C code, you have to compile it into machine code, and so you can do those protections there. or you can do runtime protections, and they have two different kinds of guarantees, different security properties, different runtime costs, all sorts of stuff. So you can't talk too long about memory safety without talking about Rust, and so we're going to talk about Rust for Joe. So Rust is a language that's came out that has a big selling point on it being memory safe. It does this through this model of ownership and borrowing. Basically means that any object is owned by a variable, and that variable can let other parts of the program borrow references to it. And there are certain rules about borrowing, like you can either have one immutable reference, like read-only reference to an object, or many of those all over the place, or one mutable reference at the same time. And you can read about these things. I'm not going to go too far into Rust. It could be its own presentation. But when you follow these ownership and borrowing rules, it does actually ensure that you won't have any of these problems because it follows this principle by dropping all your pointers when they're not used anymore. And so it sort of implements this runtime thing of garbage collection that Python and Java do, but it does that compile time, which is awesome because garbage collection is very slow. And if you want to write operating systems or databases or embedded device programming stuff, all that is very performance intensive. And so you might not have the resources to do garbage collection. So yeah, just rewrite all the software in the world. It's easy. Rust also lets you do unsafe code. Sometimes you need to do unsafe code because you're doing specific performance-related things usually. Other times, there are just certain programs that you can't do without unsafe code. All unsafe means in Rust, a lot of people think of it like kind of like, oh, you know, it's kind of a scam because you can just do unsafe code. All it really means is that the compiler cannot guarantee that it's safe. So you have to guarantee it instead. It also puts it in its own little block that says like, hey, explicitly, this is unsafe code. You have to like explicitly tell Rust like, yes, I'm going to manage this for myself, and I'm going to do it right, and nothing bad will happen. So Rust has a lot of value add, to be honest. You can search for unsafe code really easily if something goes wrong. So let's say you have like a seg fault in your Rust program. Well, there's only a couple places it's going to be because it's either going to be an unsafe code block that you wrote yourself, or maybe you're calling into C code and that C code has a vulnerability or some kind of error, really. It doesn't even have to be a vulnerability. When we're talking memory safety, a lot of these memory safety issues are not security relevant at all. So with use after free, it definitely is, but other ones are much more benign. And the other good thing about Rust is like you still have full control of the whole machine. So you can write pretty much anything that you would do in C in Rust. You can do embedded programming and all that stuff. There's nothing officially stopping you from writing anything that you would on like a microcontroller in Rust versus in C. But of course, like there's no such thing as a free lunch, and so we can kind of be honest about Rust and take like a cold shower for a minute. Rust has a big time investment. It's very slow to develop because like these restrictions that it puts on you are like pretty strong, and like there's tons of code that you can't write in Rust that you could write in C. So like in 201, you do like a linked list, and you're like, oh yeah, like one node points to the next, and that's like a mutable reference. And then like that node points to the next one or whatever. And you just cannot do that in Rust. You cannot do a doubly linked list in Rust with like mutable references like you would in C. And so honestly, it's not a hyperbolic statement to say that certain programs are just not possible without doing unsafe code. The other thing that really bites people is that unsafe Rust is not the same as C. A lot of people just sort of assume that to be the case, but there's a lot of code that you can write in C that you cannot write in unsafe Rust. And if you sort of translate the two, it might work in your C version and not work in your Rust version, which is can be very annoying. It's also still like a relatively new language, so even though you can do embedded devices and stuff like that, a lot of that stuff is sort of still in like the early stages. There might not be a lot of build tools out there. Getting your setup and development environment might be more of a pain than it should be. That's obviously something that's going to improve as time goes on. And the other thing, I mean, like the big idea with Rust is that we're supposed to rewrite all this software with it so that we have none of these memory safety issues. But rewriting software is extremely expensive. Like the Linux kernel, for instance, is 21 million lines of code about. Mozilla Firefox is, I think, like 25. It's actually larger than Linux kernel. These are like millions and millions and millions of lines of code. It's not easy to rewrite that stuff. If you wanted to like write a browser from scratch right now, like you'd literally work your entire life and not get there. It's that complex to do some of these software projects. And the other problem is it almost always leads itself to bugs, because when you're writing huge systems like that, you're going to run into the same problems. So for instance, Mozilla basically made the Rust language for Firefox. They wanted to rewrite a bunch of stuff with it to be safe. They had a CSS engine inside. You ever do CSS? Anyone know CSS? Okay. Yeah, totally. So cascading style sheets for web, it like lets you dress up your website with like fancy colors and stuff. It's why websites actually look nice. And that engine in Mozilla that renders all that stuff had a ton of CVEs. And so they were like, okay, we're going to rewrite it in Rust so that we have none of these memory safety issues. But they brought back a bug that used to be fixed in the C++ version that leaked users' entire history through SVG files. Not a memory safety issue at all. It was a logic bug. But these kinds of issues can come back when you're rewriting these huge systems. So yeah, Silo is that CSS engine I was talking about. It was a source of like many Firefox CVEs. It got rewritten in Rust. It, I think, is in Firefox stable now. And it's actually pretty good. Like, they've fixed a lot of problems with it. And they can be very sure that like tons of vulnerabilities are just not going to happen in that part of the code. And so the real value out of Rust is like, if you have the engineering time, you can break down these huge applications into smaller components, you know, where you know the vulnerabilities are probably going to be. Slowly rewrite them, and then be sure from then on out that you're not going to have these problems. The other thing that you can do besides switching to another language like Rust is enable certain compiler options. Rewriting code in another language is expensive, especially a brand new one like Rust, relatively brand new. And so there's a lot of work that's been done in the C and C++ world before Rust even existed. So for instance, there's this option called address sanitizer, or ASAN, and it basically adds checks to your code when it's compiled, so that if you go over a buffer, if you use something after it's been freed, your program will just crash, and it will tell you exactly where it crashed, and it will say, like, by the way, you have a use after free bug at this line of code, which is great because it's much better to crash when you violate safety rules. If you don't crash, you could potentially be running code that is, you know, attacker controlled, right? You'd rather have your program crash sometimes versus potentially be exploited. But the problem with ASAN, what stops it from being used in production for the most part is there's a huge performance reduction. You're adding a ton of code into your compiled binary that does all this bounds checking. And so I think in some cases it was like a 50% reduction in performance. It's great when you're developing. It's really awesome when you're fuzzing for vulnerabilities. ASAN is huge for that. But as like an end-all be-all solution, it doesn't quite get there. And there's other things that you can do, so like stack cookies. When you do a buffer overflow in 201, they're leaving out like a lot of stuff in that description because stack cookies pretty much nerf buffer overflows. Like, without an information leak, without being able to leak that cookie, like, you can't do stack buffer overflows in that way that they show you. There's also pointer authentication. So basically, whenever somebody uses a function pointer or any kind of pointer, there's a certain like cryptographic signature applied, and it basically says, when you access this pointer, are you at this point in the code? And if you're not, then it just bails out, and it replaces that pointer with a bad one, and then when you access that pointer, it fails because it's a bad pointer. So the idea with a lot of these compiler options is they don't actually fix the bugs, right? You still have that read-write issue, you still have that use after free, and it will still probably crash your code, but they're trying to prevent somebody from actually exploiting that. So this is an exploit mitigation. When they talk about data execution prevention, DEP, it's the same idea. On OpenBSD, it's called write or execute. All these are exploit mitigations. They're trying to help you so that when you get exploited, the worst doesn't happen. But of course, if you're applying it there, people find ways around these. This diagram, by the way, is not mine. I borrowed it from a DEF CON talk about Pac-Man, which is a way that blocks pointer authentication.
So I had a quick question. So you
All right.
know how with Pac-Man it specifically affects the ARM like M1 chips, right?
Yes.
So I had a question about what's the difference between point authentication and DEP. I know
Yes.
DEP is at a very high level, but I wouldn't have done to learn.
Yeah, so the idea with pointer authentication is that when you access any kind of pointer, it's sort of checking that you're doing it from the right place. And so the idea is when you're running in like a normal code path and that pointer hasn't been edited, or you aren't trying to jump to it from another place that you shouldn't be, that signature will be computed based on where you're at and what that pointer holds. If you're coming at it from another location in the program, if that pointer's been overwritten, that signature is going to fail, and it's going to replace the pointer that you're accessing with a bad one. and then when you access that bad pointer, your program crashes. And so the Pac-Man attack that this talk is about, this is a very good talk, by the way, gets around Pac by doing speculative execution stuff, kind of like Spectre and Meltdown, the same idea, kind of. And they're doing that to get around this exploit mitigation. So the point really of these mitigations is to try and stop the attacker, but they're not perfect. They're not perfect solutions like you would if you actually fix the underlying bug at the beginning. The other way that you try and deal with memory safety is you change the allocator. So when I talked about this topic at the beginning, I talked about these functions malloc and free. And they're sort of like, in 201 especially, they sort of teach these to you as a black box. Like you can just allocate memory, and it just works. And you always have enough memory, and it always works. The allocator is what actually manages that for you. It's where all that decision logic is kept. It's what says, oh, this piece of memory is in use right now. This piece of memory is free. If somebody asks for it, you can give it to them, all that stuff. And so with allocators, you can try and introduce additional security within them. And there's a couple of really great examples. Apple just started releasing security research blog posts, which is like unheard of if you are familiar with that. Apple's like never does that. It's really big news. And they released for their first one a little bit of details about their new allocator for their XNU kernel. That's the kernel that runs on like your Apple Watch or your iPhone or your Mac. And they have this new allocator called kalloc type, which does type isolation. The basic idea with type isolation is that, my speaker notes aren't coming up, the type of a pointer is the same for the entire program lifetime. So let's say I allocate a string, it gives me back an address. That address is only allowed to point to a string, and if it doesn't, the whole thing crashes. Zone sequestering is the same idea. Basically, you have a bunch of virtual addresses in the kernel. You store them in a separate zone, and whenever that memory gets deallocated from like physical RAM, you keep them in a certain zone. And so if somebody allocates data, they get it from the data zone. And if they allocate like a function or something like that, or not a function, but they allocate something else, they'll get it from a different zone. And so the idea is that when you do these allocations over time, you're only getting pointers that are supposed to point to the same type of what you're using. We had the same vulnerability a second ago that I demonstrated because we had two types, a struct auth and a string, pointing at the same memory. And if you confuse types like that, if you confuse code and data, it's almost always exploitable. And so the idea with kalloc type is that they can't really prevent every single bug in the kernel, but they do want to make it so that it's extremely hard to exploit it. Because if they make it really hard to exploit, attackers have to spend a ton of resources to try and get around it, and it might be, enough to stop somebody from getting code execution on their iPhone.
With the kalloc, right? So it's type specific, so it can only allocate that.
Yeah.
That type, right? So what happens when, let's say, a function references that pointer, and then the pointer gets casted into another type that's able to be utilized to point to something else? Is that how that works, Matt?
Yeah, so if they're doing casting, I think it gets kind of weird. My understanding is that it will allow it. It'll just be in a different, yeah, it'll be in a different type. So like the type isolation stuff is just within the allocator, and it's just keeping track of the references, I guess. Because the allocator in the kernel is the same as like the kernel code, they know what type is being allocated. It's not just like a void pointer. So they can make like intelligent correlations there and say like, okay, somebody allocated 15 bytes here, and I know that they're allocating it for this type of object. And so it isolates those. That's a really awesome blog post, though. I summarized it in 2 bullet points. It is a massive post, but to be honest, it took me like 3 tries to read it. 3rd try was a charm. It made a lot more sense then. There's another allocator called slymalloc, which is out of some my Enzo era. SLI malloc or something like that, which apparently claims to catch use after free at runtime. I read their paper, I like skimmed it, and then I read it later. It's interesting. It's very cool. slymalloc, I think, is written by like a proprietary. It's a proprietary tool. I think it's paid, but it claims to catch use after free at runtime and do all these things that were previously not solved. So I'm kind of interested in how that works. It's another good example of like more work in the space. And then for Chrome, they have their own allocator called partition alloc, which does some of these type isolation things as well, I believe, and has a lot more features as well. And so the idea with allocators is that we don't have to write the allocator for the most part. Like in 201, they never ask you to create a memory allocator. You just use the one that's on your system. And so for the most part, these allocators are not written by the application developer. It's just applied to your whole system or whatever container or who knows what. They also can apply to third-party dependencies. So let's say you're using a third-party library that you don't have the source code to. Actually pretty common. Let's say that library has a use after free bug. If your allocator can catch it, that means you don't even need to have the source code of your dependency to see that. You don't have to scan it. It can be caught by a piece of code that that you haven't written, but that you still trust. And additionally, when you're doing allocator changes, a lot of the time you don't have to change your code that much. You might not have to change it at all. And allocators have lots of different properties. Some of them are faster for certain use cases. Some of them are more secure for certain use cases. There's all sorts of different trade-offs associated. But for the most part, it's minimal or no code changes, at least by comparison to like a full rewrite. But there are a lot of other software mitigations. Hardware is an area that's really big right now in terms of dealing with this problem. A lot of memory safety issues apply to like embedded devices. For the most part, if you're running on embedded hardware, you can't run like antivirus or EDR or anything fancy that us PC users have. And so dealing with these kind of problems can be extremely difficult because you barely have enough resources to like run your application. That's why hardware mitigations are so important, because a lot of the time you won't have the speed in software, enough like compute strength to do software mitigations. Additionally, hardware is baked in. So the application developer, you don't have to worry about somebody doing the right thing. You have plenty of work to go. So let's talk about one of these. ARM has memory tagging enforcement. This is a brand new thing that they're putting into some Cortex processors. Might be on your Android phone. I think it might be on iPhone too, actually. It tags memory accesses. So this is all performed in hardware. There's no software. There are software components involved, but for the most part, the actual like performance-intensive bit is as much in hardware as possible. This is actually deployed on Android, and it catches vulnerabilities all the time. I mean, these are low-level software components. So like, what does Bluetooth on your phone, or like the processor for your phone camera that does all the fancy zooming. All that stuff can be software that might not have any vulnerability scanning going on, might not have any mitigations, might not even have like stack cookies or something in an extreme example. So doing this kind of checking in memory can be in hardware can be really effective. There's also hardware ASAN. So I talked a little about ASAN a second ago. Hardware ASAN is a lot faster. The biggest issue with ASAN in software is that it's slow. Hardware ASAN is a lot faster. And so the memory tagging enforcement technology basically works like this. I actually borrowed this from their website. When you allocate a new buffer, it tags it, and it says, okay, like you want a 16-byte character buffer, tags it as blue, it says, this is what you have access to. And if you go outside of that range, let's say you write to byte 17, so off by 1, all of a sudden you're in a completely different memory tag. And it says, okay, you're accessing something that's outside of your range, that's an overflow, I'm going to alert, and I'm going to crash your program. The alternative scenario is when you free something. So when you delete that pointer, this is how you delete free stuff in C++, one of the ways you can do it. It changes that zone to a different color and says, basically, this is freed memory. If somebody tries to access this right now, that means that they're accessing freed memory. It's a use after free. And so you can also say, we're going to crash the program here. And so basically, if you follow these rules, for the most part, it just works. And you have a lot of benefits because you don't have to, it's another layer of security at the hardware level. This is deployed on a lot of mobile phones right now. But for the most part, that's just a high-level overview of what you need to get started. These are the terms that you'll see in a lot of academic papers about this topic. I didn't cover most like C++ mitigations. A lot of C++ developers out there, and they talk a lot about this, and it's true. C++ has had like 30 years of work on smart pointers and like RAII and a whole bunch of other technologies that they use to kind of keep track of things. There's also Intel control flow enforcement, which is a really big thing. This is actually for like PCs for the most part. And so if you have like a Windows computer, it might have like a recent Intel processor, it might have Intel CFE, which basically prevents you from having like certain buffer overflows on the stack in the kernel. anytime that you return to an address, it actually checks that that address is correct with a separate entire like shadow stack. So anytime that you call back from a function, it'll see that return address. It also has a shadow stack that it maintains on its own that is not being overwritten, and you compare the two values and say like, okay, if this is the same thing I have stored here, it's good. And if it doesn't, then you can have a fault and prevent a potential exploit from running. There's also this really cool tool called C2 Rust, which is C2 Rust, not C2 Rust. You're transpiling, is what they call it, C code to Rust. So the idea with this is that, honestly, the original version is just for people that want to write Rust code, I guess. But there's ongoing research. It's actually DARPA-funded research to try and make the code that comes out memory safe. So you might be passing in C code that's not safe and then getting Rust code in the future that is, which is really cool research. Additionally, fuzzing is a really big topic. Fuzzing is the idea of sending random inputs to like a program to see if it crashes. And so for like us, let's say you have a Bluetooth stack that might be sending random packets to that Bluetooth stack trying to get it to crash. And that's important because a lot of those crashes that we're talking about might be vulnerabilities. They might actually be exploitable. There's snapshot-based fuzzing, which lets you take the entire state of a program and save it, run your test case, see if it crashes, and if it doesn't, like play the state back, essentially do a revert on the memory of a process. It's basically the same as a snapshot of like a VM. And so that's a really big area of fuzzing as well. And additionally, like fuzzing can be very slow, especially if you're doing like random inputs. Bluetooth packets or IP packets or whatever can be very complicated. And so protocol guided fuzzing is can be much more effective, where you know actually like roughly what you're trying to send, maybe the overall shape of it, and you can set specific values in the headers of a packet or set specific values in the header of like an image file or something like that. And so if you think about like wireless networking or networking in general, image parsing, all this other stuff that you don't usually have to think about, a lot of that code is written in C for performance, and fuzzing finds tons of vulnerabilities every year, CVEs, that could potentially be exploited. So that's pretty much a primer on memory safety. There's a lot of room to go in terms of solving this issue. Ton of C code out there in the world that's like, several decades old. But one thing that makes memory safety really interesting is that it's kind of a solved problem. There's solutions to it, there's mitigations. You can simply write code that doesn't have this problem. And so even though there's a long way to go, it's pretty exciting because in the end you can kind of see the end of memory safety issues in the software that we use today. So it's pretty interesting stuff. I do want to open the floor to any more questions. I'm happy to take them. Yeah, I'm going to try and see if I can't get my little questions back. Oh, man. Where's my presenter view? All right, there were no questions online. So does anybody have any questions here? We good? If you want any more information, Sarah.
Do you recommend writing any new programs in C or C++, or should you go straight to something like Rust?
Yeah, that's a good question. So there's a common thing of like, should you even bother doing C or C++? I personally, I'm like a long time C++ hater. Well, I don't actually hate C++, but like I don't write it. So I do like Rust better, I'll admit. C code is also very fun. Sometimes you need to do it. There are certain points where like, for the most part, it's very easy to do in C and it would be more difficult to write in Rust. And so for some things, but I think if you're starting like any new projects, I would definitely consider writing it in Rust first. I'd have to have like a very good reason. I think most people would say this too. Like there has to be like a very good reason for C at that point. And the more that Rust like ages and gets better in terms of like the community and like the libraries out there, and especially for like embedded stuff like the build systems and all that, the less I would recommend it. I think personally, like pretty much all software that you're dealing with can be written in a memory safe language. It's just about whether or not the effort is worth it to your use case. So yeah, I definitely wouldn't be writing any, if I'm gonna start like a low level project or whatever, and I'm gonna write like a kernel module or something like that, I would definitely personally try and write it in Rust myself. But yeah, I mean, technically speaking, you can write memory safe code in any language. It's just about the work for it. So, yeah, writing parsers, really complicated stuff, can be a good use case for Rust. Browsers, yeah. All right, any more questions? Happy to take them. Anyone in the back? All right, well, thanks for coming out. That was my last RTSec research presentation as a student here. So I hope you guys enjoyed them. They're all on YouTube, well, except for one. And I'm glad that you guys were here. Thanks.